Hello and welcome to another episode of Maths with Mrs. Banks, where we make maths fun and easy to learn. And in this video, we're going to look at the number system for mathematics grade 10 and 11. But mathematical literacy from grade 10 to 12 can also use this video as a reference. On that note, please don't forget to click the subscribe button and hit the notification bell so you don't miss out on any new videos we upload in the future. Also, if you have a question or a video suggestion, please comment down below with the topic you'd like me to cover and the grade. Or alternatively, use the email address and WhatsApp number provided in the description below. Also, don't forget to like the video and share it with as many of your social media friends on all platforms as you can. Now back to the video. In detail, we're going to look at the different types of numbers and how to classify them, a challenge for many, the decimal number format, converting decimal fractions into common fractions, otherwise known as irrational numbers, rounding off numbers, another surprising challenge, and estimating surds. We have a lot to cover, so let's start. The number system includes two big chunks. The first chunk is what we call the real numbers. These are numbers that you can find in your calculator. As long as you can find it in your calculator, it's a real number. The next big chunk is what we call non-real numbers or imaginary numbers. These are numbers you will look at in more detail if you continue with mathematics beyond metric or grade 12. But for the purpose of this course, you will need to know how to identify an imaginary number. So let's identify them. These are numbers basically that include your square root of a negative perfect square. Notice that this is a perfect square, 25, but it has a negative number in front of it. Your fourth root of negative powers of 4 and your, for example, sixth root of negative 64, for example, the sixth root of negative 64. Notice that all these roots are even numbered. This does not include, please be aware of that, this does not include your cube root, for example, of negative 8. That is equals to a real number. It's negative 2. We're going to look at that in a moment and see why. It's not part of an imaginary number system. Now let's go back to, for example, the negative square root of the negative 25. We know that 5 times 5 is equal to 25. Therefore, the square root of 25 can be written as 5. Also, negative 5 times negative 5 is equal to 25, positive 25. Therefore, the square root of 25 can also be written as negative 5. It can also be written as negative 5 because of that. Negative 5. Let me fix that. The square root of 25 can also be written as negative 5. However, notice that there is no way you can get negative 5 times negative 5 equals to negative 25. Or positive 5 times positive 5 for that matter. There's no way you can get that to negative 25. Because if you multiply two negative numbers together, they will end up with a positive, not a negative. That is why the negative or the square root of negative 25 is an imaginary number. Now let's come back to the cube root of negative 8. This is an uneven root. 3 is an uneven number, so the uneven root of negative 8 becomes a real number. It's a real number. And this is why that is the case. Negative 2 times negative 2 times negative 2, that is equals to negative 8. That is why the cube root of negative 8 is a perfect real number, which is negative 2. And you'll see exactly what type of real number it is in a moment. Now let's go to the real number system. Now imagine you had an onion, and that is the real number system. Imagine this was an onion with the layers that you can peel. But instead of peeling it from the outside, you go right into the core of the onion. That's where we're going to start analyzing the real numbers. At the very core of the real number system is what we call natural numbers. Now, these are numbers from your 1, 2, 3, 10, 100, all the way up to positive infinity. These are numbers that we teach children how to count. They're called natural numbers because these are numbers you use to count things you can see. You can see 1 cow, you can see 10 cows, you can see 100 cows, but you cannot see 0 cows. That's why 0 is not part of the natural number system. You cannot see negative 2 cows. You cannot see half a cow. As long as a child cannot explain it, you cannot see it, then it is not part of the natural numbers. That is why 0 is not part of the natural number system. Now, the next layer is the layer that includes 0. That is what we call whole numbers. They go from 0 all the way to positive infinity. Notice that so far we haven't included any fractions. So there is no half there that is included in the whole numbers either. Also notice that natural numbers form part of whole numbers, but not all whole numbers are natural numbers. 0 is not, for example, but 1, 2, 3, and all those numbers up to infinity are part of natural numbers except for the 0. All right. The next layer is what we call the layer of integers. Now, these are whole numbers. Whole numbers because they do not include fractions. They are whole. They describe a whole full entity, right? But also include negative numbers. They go all the way from negative infinity, including 0 in the middle, all the way to positive infinity to the right. Notice that integers still do not include fractions. Fractions do not belong to the integers. Integers, yes, have whole numbers in them. They have natural numbers in them, yes, but do not include fractions. Where do fractions come into the picture? Because you can find fractions in your calculator. So they're part of the real number system. They are real numbers. This is where the fractions are found. The next layer, which is the layer of rational numbers. Rational numbers are basically any numbers. Any number you can write as an integer over another integer. That is a rational number. Any number you can write as an integer over another integer. Remember, integers are whole numbers that include negative numbers, 0 in the middle, and positive numbers, which go all the way to positive infinity on the right hand side. Any number that can be written as an integer over another integer is a rational number. That includes your 0. Yes, 0 can be written as 0 over any number except for 0, because 0 over 0, that is an undefined number. Anything divided by 0 is undefined. Please don't include that. But 0 can be written as 0 over 1,000. It can be written as 0 over -5. It can be written as 0 over 1,000,000. It can be written as 0 over anything. That is 0. 0 over 20, that is 0. Square root of 9 is also a rational number because square root of 9 gives you a perfect 3. Now, 3 can be written as 3 over 1. That is why it's a rational number. So that is 3. That can be written as 3 over 1. They include your fractions. Remember, they include negative numbers, everything, negative numbers all the way to positive numbers with 0 in the middle, fractions and everything you can find, right? Except for some of the numbers we're going to look at in a moment. But before we do that, let's continue that. This includes fractions that end and fractions that have a repeated pattern. For example, 0, 8 with the dot at the top can be written as 0,8888. The 8 continues or repeats indefinitely. You can have more than one digit repeating. As a result, you'll find dots in all those digits that repeat. Also, you can have this written as 0.8 with a bar at the top, showing you that the number 8 repeats indefinitely. The next sister, it's not necessarily a layer. The next sister or brother of rational numbers is what we call irrational numbers. Now, irrational numbers include your decimal fractions that do not end, number one, and do not have a repeated pattern. For example, 1,27548. They include your pi, for example. Pi is the number. Punch pi into your calculator and equals to, you will get 3,14. This is 3,14. 594159 and so on and so on. It does not have a repeated pattern. It does not end. It also includes your square roots of imperfect squares. Punch square root of 3, you will see that you get a number that is just a decimal number that has no repeated pattern and does not end. It's 1,732,050 and so on and so on and so on. So it does not end, it does not have a repeated pattern, so it is an irrational number. So all your fifth roots of imperfect powers of 5, as long as it is a root of an imperfect power related to that root or corresponding to that root, it will be irrational. Also, if you've got an irrational number, even when it is mixed with whole numbers or rational numbers, it will become an irrational number. So 1 plus square root of 5, because that is the square root of an imperfect square, all over 2, that becomes irrational. Also, your squares of pi's, or if you square the irrational number or you divide it or you multiply it, it does not matter what you do to it. Whatever you try to manipulate, it will always lead you to an irrational number. All these are what we call members of the real number system. Both your rational and irrational numbers belong to the real number system. And real numbers and non-real numbers belong to the whole bigger family of the number system. Now let's look at some of the examples on how to classify these numbers. A question says, use the list of words below to describe each of the following numbers. In some cases, multiple words will be applicable. Okay, you've got your natural, whole, integer, rational, irrational, real, and non-real. These are the classifications you can use to classify these numbers. All right, we've got the first one is square root of 7. 7 is a real number. You can find it in your calculator. The square root of a real number, you can find that in your calculator. So that is a real number. It's real. But it is irrational because it is a square root of an imperfect square. So that's where we end, irrational. We don't move forward. 0.01, that is a decimal that has an end. So it can be written as a rational number. It is real. Yes, you can find that in your calculator. And it is rational because it is a decimal that ends. But that's where it ends. It's not an integer. So that's where it ends. 16 and 2/5. It's a real number. All right. Yes, it's a real number. Rational number, yes. It's a rational number because it can be written as 16 times 5 plus 2 over 5, which is equals to 16 times 5 plus 2. Take out a calculator. 16 times 5 plus 2, that is equals to 82 over 5. 82 over 5, yes, that is a rational number. Is it an integer? No, it's not an integer. So that's where it ends. The square root of 16 and 6 and a quarter. All right, the square root of 6 and a quarter, that is the square root of 6 times 4 plus 1 over 4. That is equals to 6 times 4 is 24 plus 1, that's 25. That's the square root of 25 over 4. Square root of 25 is 5 over square root of 4 is 2. So that is a real number. It's a rational number. Yes. But that's where it ends. It's not an integer. It's a real, rational. But that's where it ends. 0 is a real number. It's a rational number. Yes. It can be written as 0 over any other number except for 0. Is it an integer? Yes, it is an integer. It forms part of the integers. Is it a natural number? Yes, it is a natural number. 0 is part of the natural, whole numbers, not natural numbers. Whole numbers, so it's part of whole numbers. Whole numbers. That's more like natural number with a little 0. That's a whole number. But that's where it ends. It's not a natural number. There are no 0 cows, so we cannot count a 0 cow. That's why it's not part of the natural numbers. 2 pi. Pi is an irrational number. Remember, it becomes a decimal that does not repeat. Does not have a repeated pattern. It does not end. Whatever you multiply with it will end up as an irrational number. It's a real number though. You can find that in your calculator. Is it rational? No, it's not. It's irrational. -5,3 with 8 and a dot at the top. That means the 8 is repeated. So yes, it is a real number. It's rational. Yes, it's rational. It's a decimal number with a repeated pattern, but it is not an integer. 1 minus square root of 2 over 2. Square root of 2 is an irrational number, so the whole number becomes irrational. It is real though, but it is irrational, and that's where it ends. Number 9. Minus square root of -3. Square root of a negative number, that's an even root of a negative number. That is an imaginary number. It's non-real. So it is not real at all. That's where it ends. Square of pi. Pi is an irrational number. So the square of pi will be irrational. It is real though, but it is irrational. -9 over 11, that's real. Rational, yes, it's an integer over another integer, but that's where it ends. It's not an integer. The cube root of -8, yes, that is a real number. It is a real number. The root is an uneven root, so yes, it is a real number. Is it rational? Yes, it is rational. In fact, that is equals to -2. The cube root of -8 is equals to -2. So yes, it is a rational number. Is it an integer? Yes, it is an integer. Is it a whole number though? No, it is not a whole number. Whole numbers start from 0. 22 over 7, yes, that is real. It's a real number. You can find it in your calculator. Is it a rational number? Definitely. Yes, it's an integer over another integer. But is it an integer? No, it's not. So this is where it ends. 2,45897, that is a real number. But it is irrational because the pattern does not repeat and it does not end. So it is an irrational number. 0,65 with a bar at the top. That means the 6 and the 5 repeatedly repeat. In other words, it's 0,656565, and so on and so forth. Yes, it is a real number. Rational, definitely, it repeats. But is it an integer? No, it's not an integer. The fifth root of negative 32, yes, that negative 32 is a perfect power of 5. It's negative 5, negative 2 to the power of 5. So this is equals to negative 2, the fifth root of negative 3. Yes, negative 2 is a real number. It is rational. It is an integer, but that's where it ends. It's not a natural number. And that's how you classify numbers. I hope now it is a lot clearer for you and easier to classify numbers. Now let's look at the decimal number system. All right, when we look at a decimal number, we've got what we call a decimal point. That's where you're changing gears. How do you change gears? Anything to the right of the decimal point is a number that you call one by one, and you'll see why you call that. So in other words, this is comma 724069. To the left of that, that's what we call numbers that are clear now. That's your ones, your tens, your hundreds, your thousands, your until these are your billions until your gazillions. It does not end. This number would be, for example, read out as 6,781,239,465, comma 724069. Now back to the decimal point or the numbers after a decimal point. 7 tenths in this case can be written as 7/10. That comma 7 can be written as 7/10. Can be written as 7/10. And the 2 is written as 2/100. Notice you've got two decimals. This is two decimals away from the comma. So you write it to the number over 1 and 2 zeros. This one is one decimal point away from the point. That's 7/1 and 1 0. The 6 is 1, 2, 3, 4, 5 decimal points from the comma. So we'll write that as 6/1 and 5 zeros. Like that. 1 and 10. 6/10,000. No, 100,000. 6/100,000. Let me write it at the bottom here. So, and 100,000, because it is 5 decimals away from the decimal point. Now let's look at how we convert decimals, whether they're terminating or repeating, into common fractions, or what we call rational numbers. We have an example here, and it goes 10,589. This can be written as 10, that is your number, plus 5/10 plus 8/100, because that is two decimals away from a comma, plus 9/1 and 3 zeros, 1,000, which is equals to, now you find a lowest common denominator. Lowest common denominator The lowest common denominator is 1000. That is the LCD. You treat this as you would any normal fraction. The lowest common denominator is equals to 1000. So now what you do is you multiply each of the numbers by 1000. 10 times 10, 10 times 1000, that is 10,000. Plus 5 over 10 times 1000. The zeros cancel and you're left with 5 times 100, which is 500. Plus 8 over 100. 8 over 100 times 1000. The two zeros cancel and you're left with 8 over 8 times 10, which is 80. That gives you 80 there, plus 9 over 1000 times 1000. The thousands cancel out. Let me show you how that happens. 9 over 1000 times 1000. The thousands cancel out, the zeros cancel out, and you're left with 9 times 1, which is 9. And that is equal to, right, if you add all these numbers, that is 1589. So you can express this number as 10,589 all over 1000. And that's how you express that number there. Next, we're converting a repeated decimal into a common fraction or a rational number. How do we do that? We go let 0,3 let 0,333333, that is a decimal number that is recurring. You let 0,3333, let x equals to that. Let x equals to 0,3333, which that 0,3 with a dot at the top means. Therefore, if you multiply that by 10, that becomes 3,33333. Why multiply by 10? That's because when you multiply by 10, you have one digit repeating. So when you multiply by 10, you're basically shifting the comma one space to the right, and you start with 3. But they repeat continuously, so it becomes 3 all over the place. Now, subtract 10x minus x. The 10x equals to 3, 3333 recurring, and the x is 0,3333. Notice how I am putting numbers, digits in their right place. Now 10x minus x, that is 9x. That is equals to 3 minus 3, that's 0. 0, 0, 0. 3 minus 0, that is 3. So we go, that is equals to 0, 0, 0, 0, comma 3. Therefore, 9x equals to 3, meaning that if you divide both sides by 9, you get 3 over 9. If you simplify this, 3 goes into 3 once and into 9 3 times. That is equals to 1 over 3. And you have expressed your 0,3 decimal recurring as 1 over 3, a rational number or a common fraction. Next, let's see what happens when you've got repeated decimals that are more than 1. You go let x equals to the repeating or recurring. That's 5,432. 432, the 432 repeats indefinitely, and so on and so forth. Now, therefore, now we multiply by 1,000. 1,000 has 3 zeros, so they will take care of the 3 repeated decimals. We multiply by 1,000 because we've got 3 decimals recurring. If we had 2, we would multiply by 100. If we had 4, we would multiply by 10,000, and so on and so forth. So 10,000, that is the same thing as taking the decimal 1, 2, 3 spaces to the right, and that becomes 5,432, 432, 432, and so on and so forth. Now we subtract 1,000 x minus x, that is equals to 5,432, 432, 432, and so on and so forth. X is equals to 5, notice where I put the 5. Very important to put the digit where it belongs. When you're subtracting decimal, put the digit where it belongs. The 5 belongs under 2, so that becomes 5, 432, 432. So now you subtract 1,000 minus x, that becomes 999 x. That is equals to, right now we subtract 2 minus 2, these all become zeros until you get to the 5. So they all become zeros. That's 0, 0, 0, 0, 0, 0, comma. 2 minus 5, that's impossible, so we borrow from 3. We're left with 2. And we take that one. 12 minus 5, that is 7. 2 minus 0, that is 2. 4 minus 0, that is 4. 5 minus 0, that is 5. Therefore, now you divide both sides by 999. So therefore, x equals to 5,427 divided by 999. To simplify this, divide by 27 both the numerator and the denominator. 5427. We got a calculator, divided by 27. That is equals to 201. 201 over 999 divided by 27. That is equals to 37. Can leave that as a mixed number. 37 goes into 201. You go 201 divided by 37. It goes 5 times and leaves a remainder. Then you go 5. Okay, that is equals to 5. That is equal to 5. And you go 5 times 37. That will give you 185. Now you subtract 185 from 201. That will give you 16. So you go, that leaves a remainder of 16 over 37. And that's your answer there. Next, let's look at how to round off. When you're rounding off, the first thing you need to do is find out how many digits you're rounding off to. For example, round off the following numbers to the indicated number of decimal places. In some, you're required to round off correct to 3 decimals. In some, you're required to round off correct to 4 decimals. In all cases and in any case, what you do is you write a number line with the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. And then draw a line between 4 and 5. Anything 4 and above is what we call the change zone, or no change. What we call the no change zone. And everything below is what we call the change zone. And you'll see exactly what that means in a moment. Now for the first one, you go 120 over 99. Okay, when you take a calculator and you go 120 divided by 99, that will give you 1,212121. They made a mistake there. So it should be 1,21 1,21 to 1 and so on and so forth. So meaning that this is 1,2 with the 2 and 1 having dots at the top. Essentially, that's what it will mean. That means the 1,21212121. The 2 1 repeats indefinitely. All right, so what you do is you now count the number of decimal places you must round off to. So you go, after a comma, you go 1, 2, 3. and you chop it off right there. Chop it off at the third one. And then you put your left finger put your right finger on the number after the line you put. And then if the number, for example, in this case 1, falls under this no change zone, then you don't change this. Your answer becomes 1,212. But if your number falls on the the change zone, then you change this one digit up. You just add 1 to the digit right next to it to the left. So the answer to this one is simply 1, the answer to this one is 1, 212, because it does not change. And the next one, supposed to round off correct to 4 decimal places. It's pi. Punch it into your calculator and write equals to. It will give you this number. Now you count 4 decimals after a comma. 1, 2, 3, 4. Then you put the line. Now you go. What do I have to the right of the line? 9. It falls under the change zone, so that means I increase this one, number 5, by 1, so it becomes 6. So that becomes 3, 1, 4, 1, 6. Next, round off correct to 4 decimals. 1, 2, 3, 4. Put a line between 0 and 5. Then you look up the number after 0. That is 5. 5 falls under the change zone, so the 0 becomes 1. That is 1, 7321. 1, 7321. Last number, correct to 3 decimals. 1, 2, 3. Chop off after the third one. Now the digit after the chop is 7. 7 falls under the change zone. And since we've got a 9 here, it will become 0 instead of any other number, because we can't write a full 10. So that becomes 0. But then the 1 carries on to the next number. So the next number, which is 8, will also increase by 1 to 9. So we go. The answer is 2, 7, 9, 9. That's how you round off. Now the last bit, we're looking at how to estimate surds. A surd is the nth root of a number that can be simplified into a rational number. Your square root of imperfect squares, your cube roots of imperfect cubes, and so on and so forth. Example 6 says, find two consecutive integers such that the square root of 26 lies between them. Remember that consecutive integers are two integers that follow one another on the number line. For example, 5 and 6 or 8 and 9. They follow one another. They must follow one another directly. So what you do in cases like this is you write what you need to find or to define right in the middle. You want to see where the square root of 26 lies. All right. So now you list your squares. Your squares go from 1 square is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, and so on and so forth. Now you go back to your number, the square root of 26, and then find the square of a number right next to 26, but to the left. In other words, the lowest square you can find that is smaller than 26. The biggest you can find smaller than 26, and that's 25. So you go there and you go, the square root of 25 is on the left hand side. On the right hand side, you find the next square that is bigger than 26. That is 36. So you write the square root of 36 here to the right. Now therefore, you go therefore, the square root of 25, that is 5. And the square root of 36, that is 6. So 26 lies between 5 and 6. Similarly, if you have a question that goes, find two consecutive integers such that the cube root of 49 lies in between them. Now you list the cubes from the first one to one that you can say is big enough for you to compare. So that's 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and so on and so forth. All right, so let me list them like this: 1, 8, 27, 64, 125. So we can have space to write our answers. Now you write your cube root of 49 here. And then you need to now figure out what we put on the left and what we put on the right. Now we look at 49. That is our number, our reference number. The biggest cube smaller than 49 is 27. So we write that to the left. Cube root of 27. And the biggest cube, or the smallest, to the right of 49, bigger than 49, is 64. So we'll write that to the right hand side. Cube root of 64. Cube root of 64. And now you go therefore, cube root of 27, that is 3. And the cube root of 64, that is 4. Therefore, the cube root of 49 lies between 3 and 4. We've come to the end of this video. Thank you for watching. See you on the next video. Bye.